Hello everyone. Let me take a look at a pretty challenging problem in section 10.3 of Achieve. It's the 10th problem in that assignment, and it's asking you to determine the convergence of a rather intimidating looking series of the summation from 3 to infinity of 1 over n times the natural log of n to the 11th, then that entire natural log squared, minus 121n. Okay, so what I'm going to do is look at the corresponding function, and in this section we're thinking three different types of tests, whether it's a comparison test, a limit comparison test, or the integral test. To be honest, none of those three really look like a great alternative for this. I certainly didn't want to do the comparison test to try to find a function that is similar to this and then try to compare whether it's greater than or less than that. And the limit comparison test was something this complicated. Looks pretty challenging too. I chose the integral test here, and just in order to show you that the corresponding function is positive, decreasing, and continuous, notice here I've typed the function into y1 on your calculator, 1 over x natural log of x to the 11th group squared minus 121. And just by looking at the denominator, I know there's going to be a vertical asymptote at e. Please think about that. The natural log and e would cancel out, so this whole part would just be 11, and you'd have 11 squared is 121. You'd have 121x minus 121x. This function has a vertical asymptote at x equals e. Okay, so when I graphed that out, what I did, I just said it should have that vertical asymptote at e. I bet it's going to be decreasing after. On my window, I didn't want any negative x values because I knew the natural log wouldn't be defined for those anyway. I did 0 to 10, and then for my y values, I hit zoom 0. And notice it gave me this graph. So 0 to 10, zoom 0 gives me a really good looking graph here. And what I can see from this graph, yes, the function does increase initially, and it increases for a while through here and then decreases. But after this vertical asymptote at x equals e, everything is gorgeous through there. If you hit trace and then try to input in an e, notice, as expected, there is no value when x is equal to e. But if you move just to the right of that value, you see that your y value is going to be decreasing, and it's going to continue to decrease forever and ever and ever as it asymptotically approaches the x-axis. And that should make sense to you that, of course, it's asymptotically approaching the x-axis because you have 1 divided by a power of x. Clearly, as x goes off towards infinity, this function will approach 0. So there's no question that that's going to continue to go down, 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 down forever. Okay, now, so the function is positive, decreasing, and continuous for any value to the right of e. Now, I don't want to start a interval at an irrational number, and I only needed to show for 3 anyway, so I'll just say, well, since it's true for the right of e, it's certainly true to the right of 3. So I started my integral from 3 to infinity of this function, and in this problem I didn't want to, it's already difficult enough without trying to bother with creating proper notation. So the improper notation of an infinite limit, it's fine unless you're in the section where the whole point is to create proper limits. So I chose to keep infinity as a limit of integration in this problem. Now, I needed to simplify out this integral before I started trying to work with it. So the first step I did was I noticed, well, anytime you have an exponent inside of a logarithmic function, that exponent can come down in front. So I understood that this was 11 natural log of x quantity squared. Well, 11 squared is 121. 121, you have a minus 121 here. I went ahead and I factored that 121 out in front. So now I have a denominator of 121. My fraction out in front is 1 over 121. And now what's left in the denominator is just going to be x times the natural log of x quantity squared minus x. And then that, I could say, well, now I could factor an x out of that denominator and get the natural log of x quantity squared minus 1. Now, automatically when I got this step, I was thinking, ooh, okay, that's in the format of u squared minus 1. That's one of the formats we're supposed to look for. So at that point, I went ahead and said, well, let's let u equal the natural log of x. And then du is going to be 1 over x dx. I see the 1 over x dx, that will cancel out. So from this step to this step, I've went ahead and changed what's inside to this group becomes u squared minus 1. Everything else becomes du. At the same time, I went ahead and changed my limits of integration. My limits of integration here, I had the lower limit of x is equal to 3. Well, u is equal to the natural log of 3 for the lower limit. And then the upper limit doesn't change because the natural log of infinity, still infinity. So now, when I look at what I have, I notice that u squared minus 1 in the denominator. Anytime you see that, you should be thinking, well, the secant substitution should be helpful here. So if I let u equal to the secant of theta, I know du is going to be derivative of that, secant theta tangent theta d theta. And so now that denominator, u squared minus 1, would become secant squared minus 1. Well, secant squared minus 1 by definition is tangent squared. So now I can say, well, then that denominator is going to become tangent squared theta. The numerator becomes du, which is secant theta tangent theta, and I chose to put my d theta at the very end. Now, of course, that tangent theta simplifies with one of the tangent thetas in the denominator, and so I'm left with secant over tangent. Well, secant over tangent would not be helpful, so you'll see what I did in the next step was I went ahead and said, well, that secant theta is the same thing as 1 over cosine theta. You're dividing by a tangent theta, which means you're multiplying by a cotangent or multiplying by cosine over sine. I got everything into cosines and sines. I see that the cosines cancel. I would have the integral of 1 over the sine of theta. Now, that 1 over the sine of theta is the same thing as the cosecant of theta. And then at that point, that's not something that's easily integrable, though we could do it. But I just went to the chart and said, well, finally, now I can say that the integral of the cosecant of u du is the natural log of cosecant u minus cotangent u plus c. So using the table of integrals to assist, and I put number 14 over my equal sign to reference the table of integrals. This is equal to the natural log of cosecant theta minus cotangent theta, and I'm evaluating that from the natural log of 3 to infinity. Now at that point, I needed to plug back in my terms of u because I needed to go evaluate from u equals the natural log of 3 to u equals infinity. Up here, I drew my trig triangle. If u is equal to the secant of theta, then I know that the cosine of theta would equal 1 over u. Cosine of theta is adjacent over hypotenuse. So I draw a trig triangle here with the adjacent side 1, a hypotenuse of u. We know the opposite side has to be the square root of the hypotenuse squared minus the other side. And please remember, in your trig triangle, the expression from the original problem always has to pop into it, and it does. And so now, whenever I say, okay, we have the cosecant of theta, well, that's going to be 1 over the sine. Sine would be opposite over hypotenuse, so cosecant's hypotenuse over opposite. That's where this comes from. The cotangent's just the reciprocal of the tangent, so it's going to be instead of opposite over hypotenuse, instead of opposite over adjacent, it's going to be adjacent over opposite, the 1 over the square root of u squared minus 1. So I get my cosecant and my cotangent back into terms of u. At that point, guys, it's just evaluating it. So whenever I evaluate at infinity, I'm just thinking, well, if I allow u to approach infinity, then this first fraction, it essentially becomes u over u, because the square root of u squared is the same thing as u. So I would have infinity to the first over infinity to the first. That's just going to reduce down to a 1. In your second term, 1 over a number approaching infinity is going to go to 0. So I have the natural log of 1 minus 0 for that first one, and then on the inside of that, and all of this should still be inside of a natural log. I forgot that in this next step. Ooh, so 100, I'll say natural log of all of this group. Then when I'm subtracting out the lower limit with the natural log of 3, when I plug the natural log of 3 into these expressions, I got these two numbers here. Now, the point being is that this ended up being a finite answer. So with this finite answer here, I know that this integral converges. Now, whatever answer it converges to is irrelevant. The whole point is that I'm showing that it does have a quantitative finite answer. And so if the integral that has to account for every single possible x value converges to some finite answer, then we know that the series that only accounts for whole number values of n is also going to converge. And that's what I said right here. Since the integral converges, then we know the corresponding series must also converge. Okay, hope that helps out with that problem. Certainly not an easy one there, but a fun one.